Essay questions for the Unit 4 exam. First question, explain how solutes and water are reabsorbed in the kidney tubules. Be sure to include the reabsorption of sodium, glucose, water, chloride, calcium, potassium, etc. Include in your discussion how the various solutes are reabsorbed and the concept of renal threshold and saturation. Discuss the process of filtration, and in your discussion, describe the filtration membrane in the renal corpuscle and the pressures involved in filtration. Discuss how blood flow may be regulated to the glomerulus. Describe what GFR is, and then explain the principle of clearance and how it is used to estimate GFR. So, the rough drawing of a nephron here, Bowman's capsule, proximal tubule, descending, ascending, and then collecting duct over here. Reabsorption of filtrate begins in the proximal tubule and is where the majority of reabsorption occurs. It alone reabsorbs 70% of filtered water and salt, as well as all of the filtered glucose. The main pathway for reabsorption is through secondary active transport, where proteins are carried back into the blood by being tied to sodium as it goes down its gradient, and that sodium gradient is formed through the work of the sodium-potassium pumps. And the transport proteins used for secondary transport are very specific, so it is possible that they become saturated if there's too much of their solute transfer. In the case of glucose, there are many more transporters available than are needed at any normal glucose levels to reabsorb everything. But if these transporters are saturated and glucose levels rise well above normal parameters, glucose can end up passing through proximal tubule, and some may end up in the urine, and that is a guaranteed sign of diabetes. And the limit for these transport proteins is different for each one, and that limit is the renal threshold value. For glucose, the limit is around 200 milligrams per deciliter, where normal blood levels for glucose are around 100. And many other solutes are reabsorbed, including bicarbonate. With the coupling of CO2 and water and bicarbonate and hydrogen, that leads to the net absorption of bicarbonate out of the nephron back into the blood, and the net excretion of hydrogen ions into the nephron. And because of the gradient of sodium bringing so much sodium into the cell, it gives the interior of these cells a positive charge that also works to draw in negative ions like chloride. And this difference in charge from cell to inside of the nephron also helps to attract water to move it intracellularly and paracellularly between them here. While water follows the sodium gradient paracellularly, it also drags other ions with it, such as calcium and potassium, and that is known as solvent drag. So, up here, to get solutes into the nephron, they need to be filtered first. And they're filtered through a membrane before entering the Bowman's capsule here. This filter is charged and has very small pores, so only uncharged and very small molecules can pass through it. And filtration is facilitated by the pressures of the blood pushing into the nephron. Hydrostatic pressure from the glomerulus is at 55. So start another drawing here. This is the glomerulus carrying blood to the nephron, Bowman's capsule. So we have 55 millimeters of mercury worth of pressure, pushing blood, solutes, everything in. And then hydrostatic pressure from Bowman's capsule is 30. And osmotic pressure from proteins that remain in the blood draw water back with another 15 millimeters of mercury worth of pressure. So net movement of fluid is into the nephron with 10 millimeters of mercury worth of pressure. And the 55 millimeters of mercury is provided by the glomerulus, is regulated by the vasodilation and vasoconstriction of the afferent and efferent arteries, leading to and out of the Bowman's capsule. And GFR is glomerular filtration rate. GFR is regulated by the constriction and relaxing of the arteries leading to the glomerulus. And part of this regulation comes from smooth muscles and their intrinsic ability to constrict when stretched. And that happens because they have stretch-activated calcium channels that allow the vessel to constrict on its own whenever it feels that it is being stretched in order to maintain homeostasis. And this works well to counteract high blood pressure in the glomerulus. But with lower blood pressure, the tubuloglomerular feedback system is used. And this system utilizes macula densa cells at the junction between the ascending and distal tubules. So, back up to this drawing. As this afferent artery is coming up to the Bowman's capsule, it will pass by another section of the nephron here. And this is where the macula densa cells are. And so this system utilizes macula densa cells, which monitor the concentrations of sodium and chloride ions inside of the filtrate here. And if these cells detect lower than normal concentrations of these ions, they release nitric oxide, which acts on the nearby afferent artery to vasodilate it. And this dilation allows more blood to the nephron to increase filtration. And the macula densa cells can also induce vasoconstriction by releasing adenosine when the cells detect high concentrations of ions. Then clearance is a measurement of the rate at which a substance is reabsorbed into the blood and excreted through urine. If 100 milliliters of filtrate entered the kidney and all water is reabsorbed but none of the solute, then the clearance for that solute would be 100 milliliters per minute, because all of it was excreted, none went back into the blood. So clearance can be calculated with this equation here. So in this, Cx is the amount of plasma cleared of a substance per minute. UX is the concentration of X in the urine, X being whatever solute we are attempting to measure. V is the volume of urine over time, and px is the plasma concentrations of X. In order for a solute to match the GFR of in order for a solute to match GFR, a set of criteria must be met. The solute must be small and uncharged in order to be freely and completely filtered out at this point. And the solute must not be reabsorbed. It must not be reabsorbed, secreted, degraded, or produced by the nephron. And so there aren't many things that match that, but creatinine is a solute that meets those criteria. So the concentrations of creatinine in the urine can give a good estimate of the function of the kidneys. Normal concentrations of creatinine in the urine are 97 to 137 milliliters per minute. All right, question 2, explain tubuloglomerular feedback. Explain the renin-angiotensin-aldosterone system. Describe what happens at the cellular level with ADH and aldosterone. In part 2 of the essay, explain how the loop of Henle is used to establish and maintain the renal medullary concentration gradient. Explain how this gradient and ADH can work together to excrete urine of different concentrations. So the tubuloglomerular feedback is accomplished through specialized cells called macula densa cells, located between the ascending and distal tubules. The macula densa cells detect concentrations of sodium and chloride ions in the passing filtrate and releases hormones that act on the nearby afferent artery to change blood flow to the glomerulus to make necessary changes to the filtration rate. Then, the renin-angiotensin-aldosterone system is used to retain sodium, which also causes more water to be reabsorbed from the kidney. If a decrease in GFR is detected or a general decrease in blood pressure is detected, then renin will be released into circulation. And then renin will act on a hormone called angiotensinogen, which is produced by the liver. And then renin changes it into angiotensin 1. And then angiotensin converting enzyme then changes angiotensin 1 into angiotensin 2. And this ACE hormone can be found in high concentrations in the capillaries of the lung. The main effects of angiotensin 2 are stimulating the release of aldosterone from the adrenal gland and constricting of the efferent arterioles. That would be the arteries leaving from this point. It also acts as a potent vasoconstrictor of systemic arterioles throughout the body and induces the release of ADH. And then aldosterone specifically acts to increase the output and total number of sodium-potassium pumps. So these will increase the reabsorption of sodium and excretion of potassium. The constriction of the efferent arterioles will increase the pressure of the glomerulus and increase GFR, which increases sodium filtration and reabsorption. And finally, the release of ADH activates aquaporins to allow water to freely move in order to follow the reabsorbed sodium. All right, up next is the loop of Henle. So the loop of Henle is able to establish a renal concentration gradient is because it is permeable to water on one side and permeable to solutes, only solutes on the other. So on the descending side, only water can leave. And on the ascending side, solutes can leave. So on the descending side, only water is able to leave. So as water leaves, the concentration of the filtrate increases as it descends the loop. And then on the ascending side, only solutes are permeable, so the concentration goes back down as filtrate goes back up the loop. And ADH and this gradient, once we reach the collecting duct, so ADH and this gradient are used to control the concentration of excreted urine by changing the permeability of water in the collecting duct. So ADH, when released, causes the collecting duct to become more permeable to water, and as water travels down this collecting duct, the surrounding concentrations of solutes draws the water out through osmosis. Alright, question 3. Explain all of the membranes, pressures, and mechanisms that make negative pressure ventilation possible. Describe what a pneumothorax is and how it occurs. What is surfactant? How does a lack of surfactant impair ventilation? Explain how CO2 is transported in the blood. Describe O2 transport in the blood. Include a description of the oxygen-hemoglobin dissociation curve and factors that influence the affinity of hemoglobin for oxygen. How do these factors affect the oxygen-hemoglobin dissociation curve? All right. So the lungs are able to create negative pressure in the thoracic cavity by expanding and contracting to move air in and out. The lungs are prevented from collapsing in on themselves due to the fluid that lines the pleural cavity here, outside of the lungs, but inside the thoracic cavity. And this adheres the lungs to the walls of the thoracic cavity, while allowing the two surfaces to move freely against each other. And this adherence to the thoracic wall prevents the lung from collapsing while the lungs are under tension to contract. The pleural membranes allow the two surfaces to slide with very little friction, and the serous membranes are responsible for secreting the serous fluid that adheres and allows the smooth movement of the lungs against the wall of the thorax. And so pneumothorax is a condition where air is able to enter the pleural cavity and negates the negative pressure created between the lung and the thoracic wall. And so because the lung is under constant tension of its own to pull in, when air gets in here and breaks the seal of suction between the lung and the thoracic wall, it leads to the collapse of the lung. And this condition can be caused by damaged lung that allows air to escape into the cavity, stab wounds, gunshot wounds, anything that could allow air into this cavity. Then within the lung, surfactant is a substance that interferes with the molecular bonds water can make with itself, which lessens the surface tension of the water. This is needed since the interior of the lungs have thin layers of fluid to keep them healthy, and pressure within an alveolus is determined by this equation here. And so this is pressure within the alveolus. This represents the surface tension of water within it, and this is the radius of the alveolus. So this equation shows that any alveolus smaller than others, this goes down, the overall number produced here goes up. So any smaller alveolus has a higher pressure and no air will flow into it. And the ability of surfactant to reduce surface tension is what is able to equalize this pressure. So more surfactant causes this to go down, which will equalize pressure. And now CO2 has three main modes of transport through the body. 7% is transported simply as it is dissolved in the blood. 23% is moved as it is bound to hemoglobin, and 70% is transported as a bicarbonate ion. And then oxygen is transported mainly as it is bound to hemoglobin, since it cannot dissolve as easily in water. And this ratio of hemoglobin-bound oxygen to dissolved oxygen is around 99% to 1%. Thus, factors that affect the binding of oxygen to hemoglobin are very important. So the saturation of hemoglobin is graphed with the partial pressure of oxygen in the body. And at rest, the hemoglobin is saturated usually above 75% and pressure above 40 millimeters of mercury. And this curve can be shifted by different stimuli. Lowered pH, increased carbon dioxide, increased temperature, and increased 2,3 DPG all shift the curve to the right, since they lower hemoglobin's affinity for oxygen. and then increased pH, decreased CO2, and decreased temperatures all shift the curve to the left since they increase the affinity of hemoglobin for oxygen. Finally, question 4, explain Dalton's law and Henry's law, and how these laws are used to explain the partial pressure of oxygen and CO2. Explain the alveolar gas equation and how the information it gives us might be used. Finally, explain ventilation and perfusion ratios and give examples of what might cause these ratios to change. In part 2 of this essay, explain total pulmonary and alveolar ventilation rates and describe why slow, deep breaths are more beneficial than rapid, shallow breathing. In part 3 of this essay, describe COPD and restrictive lung disease. Between these two diseases, mention what emphysema would be, and then explain the mechanisms of air trapping. So Dalton's law states that the partial pressures provided by different gases all add up to the total pressure within a system. So within our atmosphere, nitrogen makes up 70% of available gas, oxygen around 21%, and CO2 another very small fraction, and others fill out. And so each of these have their own pressure, and all together they add up to the 760 millimeters of mercury worth of pressure at sea level. And so the percentage makeup of an atmosphere with the total pressure can be used to calculate the pressures provided by specific gases. And then Henry's law describes what influences whether a gas will dissolve into a liquid. Some of these factors are the partial pressure of the gas surrounding the fluid and the solubility of the particular gas. For example, CO2 is 24 times more soluble in water or plasma compared to oxygen. Then to summarize, gas pressure times coefficient of solubility equals the dissolved gas concentration. Then alveolar gas equation is so that's it there. So in order from left to right here, PaO2, that is partial pressure of oxygen in the alveolus. This is the fractional concentration of inspired oxygen, which is this here. Out of all the gases that are breathed in, 21% is oxygen. So at sea level, this represents 0.21. Then this is atmospheric pressure, water vapor pressure. This is arterial pressure of carbon dioxide. And this is the respiratory exchange ratio, which is 0.85 in normal cases. The ventilation perfusion ratio, or VOVQ, is the air that reaches the alveoli over the blood that reaches the alveoli. So it represents the amount of oxygen that can actually diffuse into the blood. Things that could lower this ratio must reduce the ventilation of the lungs. This could be bronchitis, asthma, or pulmonary edema. And then things that increase this ratio could, they must decrease the perfusion or the blood supply through the lungs. An example could be a pulmonary embolism that restricts blood through the lungs, preventing them from picking up oxygen. So total pulmonary ventilation is breaths per minute times tidal volume. And tidal volume here is the total volume of air brought in from one breath. And then alveolar ventilation is similar, but only considers the oxygenated air that reaches the alveoli. So lungs branch a lot, and as air is brought in, only the air that is inside of the alveolus is able to exchange gases. Everything left up here is still oxygenated and represents a dead space. So even as we breathe out, some of it still remains inside here. Breathe in, so some volume is not used within the lungs. So slow, deep breaths are better since they draw in more air and increase alveolar ventilation. And then for the diseases, COPD stands for chronic obstructive pulmonary disease, and 80% of cases of this are caused by smoking. So smoking, among other factors, damage the walls of the alveoli, making them much less elastic. And since the lungs rely heavily on the natural elasticity of the alveoli to constrict and push air out, this change makes it very difficult for someone with this to breathe. And this change in elasticity also causes airways to collapse before air can be pushed out, trapping air within the lungs. So if these walls are weakened, they close before air can exit.